So this is part B of our two rocks in space colliding problem, and it says that in a different collision, the two rocks that we had uh, will have the same initial parameters, but this time when they collide, they attach and move off together in the same direction. Whereas the first time when they collided, they didn't stick together and they ended up with two different final velocities. So part B is now asking what is the final velocity of the attached rocks. So instead of solving for the final velocity of one rock, now since they have attached, we are solving for one big final velocity that includes both rock 1 and rock 2. And again, just like part A, we have these initial values that we were given, including the masses of the two rocks and both initial velocities. And we're no longer worrying about that final velocity of rock 1 that was given in part A, because again, we are looking for the combined final velocity of the two attached rocks. So just like last time, we are going to revert to the momentum conservation principle. And now this momentum conservation equation as a whole is going to look a little bit different, just formatted a little bit differently. We can have the initial state, the initial momentum of rock 1 plus the initial momentum of rock 2 is going to equal, and then in the final state, just to make things easier for us, we are going to have the mass of rock 1 plus the mass of rock 2, and this is in parentheses, times the final velocity overall, because both of these combined masses as one big total mass times our final velocity is that overall final momentum. So we're just gonna again bring this down and put in all of our values that we know. So our first mass, our mass of rock 1, 3,000, and then times the initial velocity of rock 1, 20 meters per second, plus, and then this momentum is going to be 0 again because our initial velocity of rock 2 is 0 meters per second. This together is going to equal, and then we're going to add the two masses together, so 3,000 plus 1,000, and then times the final velocity, which we are going to be calculating. So we just do our simple math. 3,000 times 20 is 60,000. This is going to equal 4,000, which is our total mass, times our final velocity, and then we divide by 4,000 on both sides, and we get that our final velocity of the two attached rocks is 15 meters per second. So where we had the two final velocities in part A separate from each other, now we just have one big colloquial final velocity.